So a binomial distribution then is when we're looking at the binomial probability distribution, and so we can ask for a particular value of x, what the probability is of us getting that value of x in a study or in a randomly chosen person, and we're going to do it based on the study. So the distribution formula looks like this, and it has P of x, which is the probability of success on a single trial, and the x is the number of successes in n trials. So what we're saying then is if we look at P of 2, we're saying we want to know the probability of 2 successes in n trials. So that would be an interpretation of that. And it is also exactly 2 successes. It's not less than 2, up to 2 successes, or more than 2 successes. It's exactly 2 successes. So we're going to look in a little while how you have to calculate to figure out if you want less than 2 successes or more than. We have to do different things. But for right now, we can say that P of 2 is going to give us the probability of exactly 2 successes in n trials. And that's the left-hand side. Now, the formula itself has that n choose r, and it's actually n choose x, and you can also use the NCR button on your calculator, the n choose r, and then that's the thing in the parentheses there, and then we have P to the x, so that's remember the probability of successes on a single trial, and we're raising it to the x, which is exactly the number of successes we were looking for. And then we have the q to the n minus x. So q is the probability of the failures, and the n is the number of trials, and the x is the number of successes that we're looking to find the probability for. So x is plugged in 2 different places on this product here, but then it's also in the n choose r. It's the r part of the n choose r. So hopefully I didn't make it any more confusing, but remember, if you need to do the n choose r by hand, this is the formula. And remember, you can also use the n choose r on your calculator. You might need to push the probability button first and then choose it from the menu, or you might just have an NCR on your calculator. So, and I think if you need to do it by hand, remember you have the 5 factorial, meaning 5 times 4 times 3 times 2 times 1. All right, so if we want to know for a binomial random variable, we can find the mean. This is a little different than anything we've done before, but we can find the mean for that distribution, and it's going to be the n, or the sample size, times the probability of success. If we want to find the variance, it is just n times the probability of success times the probability of failure. And then standard deviation, of course, take the variance and take the square root of it. So those are different than for just a regular set of numbers, because it is a probability distribution for a binomial random variable. So it's a little bit easier to calculate some of the things for it, but we have to make sure that it's really a binomial random variable. So here we have toss 3 coins, count the number of heads x. Construct the probability distribution for x. Determine mu and sigma for the binomial random variable x. So x is defined to be the number of heads. So x is the number of heads. And n we're tossing 3 coins, so N is 3. So I have 3 trials. And then I'm looking at the probability of success for each trial. So the P is going to be 0.5 for each trial. And that makes my Q also a 0.5. And the probability distribution for X. And I also want to state that success is tossing heads. Okay, I want to show you this 2 ways. The first is by hand. So if I do this by hand, I can think about my first toss is going to be either heads or tails. And then my second toss is going to be either heads or tails. And depending on what my first was, I need to write it another time. And then my third toss heads, tails, heads, tails. You can see we're getting cramped here. Heads, tails, heads, tails. So if I'm looking for toss 3 coins and count the number of heads, I have several tosses that have heads, and if I look at them in the sample space, I have heads, 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 tails, heads, tails, heads, heads, tails, tails. And that should have gotten me done heads, 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 tails. That should have gotten me halfway there. I got that one, that one, that one, and that one. And so now I have left yet. I have tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. And that's my sample space. So now I can look at what is the probability for each of those outcomes. And each of them, the probability for each is going to be 1 out of 8 because there are 8 of them. And then I need to think about the, I think I can go down a little. Maybe not. I need to think about what's success for this, and so that is going to be just a small table where I have my X's, which is the number of heads observed, and so the smallest number of heads I could observe is 0, and then I could do 1, 2, or 3. I'm only doing 3 tosses, so 3 is the most heads I could observe, and then this could be the probability of observing that number of heads, so I can see for all 3 I have it just 1 time out of 8 since they're all 1/8 likely. This has 2 heads, this has 2 heads, so I'm going to put little check marks when I take care of them. So if I'm counting the ones with 2 heads, I have 1, 2, 3 of them, so that's going to be 3/8. And where I only have 1 head, there I have 1, 2, 3. And so that one is 3/8. And then where I have no heads, that's just this last one here, and so that one is 1/8. So I can see my probability distribution there. That is the by hand method, and you can certainly do that with 3 heads or 3 coins being tossed. Not a big deal. But let's take a look at how we could do the same calculations but use our formula. And our formula looks like this. P of x equals n choose x, and then we have little p to the x times little q to the n minus x. And what I'm going to be finding first is the probability of 0 heads showing. So that's the first thing on my chart that I did by hand in that probability. So I'm going to plug that in. My n, remember I'm doing 3 trials, so I have 3 choose 0. And then the probability of success is 0.5, and that's raised to the 0 power. The probability of failure also 0.5 raised to the 3 minus 0 power. So 3 choose 0, if I do that on my calculator, 3 choose 0 comes to 1. 0.5 to the 0 comes to 1, anything to the 0 power. And then 0.5 to the third, that's going to give me 0.125. And when I multiply it by all those ones, it's going to give me probability of 0 heads showing is 0.125. Now, wouldn't it be nice if I knew if 1/8 and 0.125 were the same? Well, they are. So I could divide it out on my calculator. That does come to 0.125. And 3/8 comes to 0.375. And 0.375. And 0.125. So it looks like I've gotten the same value that I got from working it out by hand by using this probability distribution formula. So that's kind of cool. And now I want to try another. I only have a few, so I can do them all. So I have probability of seeing 1 heads is 3 choose 1 this time, times 0.5 to the first times 0.5 to the 3 minus 1, which is 2. And so 3 choose 1 comes to 3 times 0.5 times 0.125. No, times 0.25, which ends up being 0.375. And that's the probability of seeing 1 heads, exactly 1 heads in 3 trials. So the probability of seeing 2 heads in exactly 3 trials, just plug in a 2 instead of the 1, still have n equals 3, and we're multiplying by 0.52 squared times 0.5 to the 3 minus 2, so to the first, and that's going to give me 3 choose 2, gives me a 3, times 0.25 times 0.5, which ends up also 0.375, and that's the probability of seeing 2 heads. So far we're matching what we did by hand over here, and we have one more to do, and that's the probability of seeing exactly 3 heads in 3 tosses of a coin. So 3 choose 3, 0.5 to the third, and then 0.5 to the 3 minus 3, which is going to give me 0, so this whole thing is going to change to 1. And then I have 3 choose 3, which is 1. There's only one way to choose 3 if you have a set of 3. 0.5 to the third is going to give me 0.125. And then I have that 1 from above the 0.5 to the 3 minus 3. So I end up with 0.125 is the probability of seeing exactly 3 heads when you flip 3 coins. So what I wanted you to see here is that using the probability distribution formula, we get the same results without having to list out all of the possible cases. And of course, if it's only 3 coins that you're tossing and there's only 2 outcomes per toss, it's not an unmanageable task to do by hand, but keep in mind that this probability distribution formula works for small samples, but it also works if I wanted to check if I was tossing the coin 5,000 times, what would my probabilities be for each of the number of heads that I could come up with. And you can calculate it much more quickly using this probability distribution formula. And you don't always want every one of these. Sometimes you only want one. And what's the probability of getting exactly 7 heads if I'm tossing the coin 10 times? So you can find those answers using the probability distribution formula. Now, unfortunately, we're not quite done, because this problem is also asking for us to find mu and to find sigma. So we need to use our little formulas that we have from above, and mu is n times p. So n in this case is 3, and p is the probability of success, so times 0.5, and that means my mu is 0.125, right? No? 1.5. That's what I was thinking. Okay, and then I need sigma, and that is going to be the square root of n times p times q. And for this case, it's going to be n, which is 3, times 0.5 times 0.5, which is my q. And when I multiply all those out, I get 0.75, but I need to take the square root, so I'm squeezing it in, I'm sorry, 0.75, and then when I take the square root, I get 0.8660 rounded. So there is my sigma. So if I need to write this a little better, so what I have then is my mu. Seriously? Mu is 1.5 and my sigma is 0.8660. There we go. So the probability distribution for x, by the way, is this chart right here. And we could make that by hand in this case, or we could use the probability distribution formula, which we did over here and got the same results, but this would be the distribution here.